Okay, let's continue where we left off. Before start with this, in order to have a good understanding of your individual assessment, the formative assessments, please watch the Eurocode 7 explanations. Then you can understand what is the characteristic, what is the design, what is the partial factor, what is the model factor, and the correlation factors. Based on the Eurocode 7 explanation video, in tutorial, I will go through the practical design problems. It is also a simplified version, but in your the assessments, in the real cases, we have multiple layers. Even some layer is clay, some layer is sand. Okay, in sand, we also have skin friction and bearing capacity. The summation of these two is so-called highest bearing capacity. This bearing capacity can be determined by effective stress beta methods, sand, coarse materials. Every water drain out, able to drain out. Then SPT, CPT result has something to do with our beta methods. Well correlate with sand material properties compared to clay. That's why the bearing capacity of the pile in sand, we frequently use in situ test results, SPT and CPT. And then sand material looks like drain materials. So mostly go-to approach is beta method. Point bearing, okay. Here, now we are in point resistance drain condition here, right? Oh, it is still sigma and Q, right? Particular something. Okay. Why? This is our general bearing capacity equations. CNC, QNQ, 0.5 gamma, B and gamma. Insignificant. And insane cohesiveness. Cancel out. Only the term remaining is Q and Q. Q is the particular effective stress. So the issue is how to obtain NQ. The driven pi is sigma prime times NQ. Makes sense because we just discussed, ball pi. Why? 0.5. Weird. Same pi. Why? Driven is just as it is, but why ball pi 0.5? Factored by 0.5. Only halfway, right? Unfair. Anyone knows? Just give it a try. Any answer is acceptable. Okay. Now we can just move. So the issue is the NQ varied from number 8 to 2000. 8 to 2000 in terms of the friction angles. Devier, Meyerhoff, Scampton, Hansen, Terjagi, Basic. Wow. Which graph are you going to use? I can't decide. But these bearing capacity factors inferred from certain theories based on shallow foundations, the load transfer mechanisms, but mostly punching shear failure modes because our pipe's diameter is too small. So probably it failed in the punching shear failure modes. Skin frictions. Now we are in the skin frictions. Short frictions, drain conditions in sand here. Simple, same. Vertical effective stress times beta. Beta affected by horizontal earth pressures and interface. The friction, the roughness of interface. But in particular in sand, the mechanism is not well understood, still uncovered yet. It is because the shaft's frictions strongly depends on current, the particle effective stress levels. And then also we have significant effects of OCR near the surface, near the pile heads. And then there should be some volume changes, adjacent high. Clay is not a big problem. Only sand, we have certain issues. That's why currently many researchers working on the shaft skin frictions behaviors. My Korean academic supervisors working on this wrote many research papers on these areas. Okay, still we are in the beta methods. K naught is the at rest lateral expression coefficients. I'm not moving, just stationary. Then the coefficients of the lateral expressions can be represented by 1 minus sine B prime internal friction angle. And then OC over consolidated soil conditions. This one times OCR square roots. So K naught OC means 1 minus sine sigma prime and OCR square roots. So what is the recommended values? Yes, we sometimes use Cool-High method, skin frictions, Ks, lateral pressures, vertical effective stress, delta is the friction roughness. How do we derive such relationships? Can be obtained from, is it sand or is it rough concrete and loose sand, dense sand? Then is it displacement pi or bore pi, jetty pi, according to the our project site's given conditions? We can navigate appropriate values from mostly around here. 111, 0.9, 1 or 0.79, 1.25. 25% decrease, 25% increase, 20% draw down, as it is, something like that. For example, now my internal friction angle is 30 degrees. What is the roughness of the interface? 30. When? Now I'm dealing with sand and rough concrete. My current end-rest lateral aspiration coefficient is something like 0.7. But when you're dealing with large displacement piles, driven piles, you can use same numbers. But is it dense? Yes, times 2, 1.4. Now we are dealing with in-situ test results. Actually, you can put it here also can, because it depends on, it doesn't matter of the drain or on-drain conditions. Yeah, n value. Before using n value, we have to correct this n value by energy, 60%. And more efficiency, borehole diameter factors, sampler factors, load lengths. Wow, a lot of things to consider, but just follow your charts, follow the step by step, not that complicated. Because all value is already prepared. And then equation, how we correct your SPT value. Probably Kisojiban iLab gives you certain good perspective. Driven pi, ball pi, from Meyerhoff in the same year proposed simple equation using SPT value for point resistance, shaft resistance, point resistance and shaft resistance. But important thing is we should have certain cap. Because sometimes our end value is more than 100. Certain area we face rock very early. The expected value is now is 200. So you key in here 200 times something more than 1,000 kilopascal, megapascal, something like that. We are not supposed to use these values. We have to cap it up. And also after Meyerhoff, certain empirical chart for driven and ball pi. For the previous one is point resistance, is side resistance, shaft resistance, driven and ball pi. Yo, still here's the 400, 120. Why? This is my questions. Why ball pies point resistance is halfway of the driven pi? Simple. Uncertainties of the end bearing. Depends on workmanship. You know, ball pile means we do pre-borehole, right? Excavate. Then we come down there and then see, oh, our end bearing soil is quite clean. Then pouring concrete. We can't. Just excavate, pouring concrete. So we couldn't check whether end bearing is 100% cured and then circular shape as we intended. We don't know. A lot of uncertainties in terms of the installations, and strongly depends on workmanship of site engineers. That's why we draw down the effect, the bearing capacity. compared to driven. Driven one is just hit, driven to the certain layers. It could be good contact with skin and soil and very tall and then bottom soils. Uncertainties. Now we are supposed to use CPT value. This is CPT. We read off the resistance at here and here. QC tip is the cone resistance at tip. Cone resistance average along the shafts. We directly use the number to get driven piles, bore piles, point, and shaft resistance. Actually, it is one of the last year exam questions. This information was given and calculate your piles, shaft, and bearing resistance based on the readings of the cone penetration tests. Given everything, so what you can do is just implement, read off the data, and then calculate your shaft and toe resistance, and then compare with your design actions and calculate pile length and number of piles. Simple arithmetic calculations. For this year, yeah, I changed the questions. Yeah. But simple thing is something like that. I just want to tell you, for example, this is your pile length, but don't know. L length pile, you don't know. And then skin friction, Fs is 300 kilopascal. And then end bearing is 800 kilopascal. Right? Given your certain conditions, times pi E. This is your shaft resistance. Kilonewton. This one times your end bearing resistance in kilonewton. You know pi, right? 3.14. 3.14. Pi diameters 1 meter. Only LP is unknown. So, for example, 285.7 times LP plus the Pascal, your design actions. For example, GK, QK times 1.3. So which is the, for example, 11,000 kilonewton. So your pile length. You can determine your pile length. Only unknown is your pile length. This is the way you design your pile length. Not enough. Not enough. Here is the field. Residual soil. Only 1 meter weathered rock. but your LP is not enough, you increase high length. Socket it more and more. It means your end bearing significantly jump up, your shock resistance in the rod also increase. The field materials 10 meters, residual soil 11 meters, in total 21 meters. LP rod. Times 21 plus LP. Your equation looks like that. Singapore Code of Practice. From the CPT, we simply use the outcomes from CPT, skin frictions and end bearing. So in order to know a part's performance, bearing capacity, we do pilot tests. This is a H part, still H part. We attach a strain gauge here. And then this is the speed values. Then we do load tests with certain loading conditions. Load settlement curve. The Professor Wang Kai-Sin, former NTU professors, former our SIT professors, now is totally retired. He is the pilot expertise conducted in pilot tests, reaction pile, our test pile, here is the load cell, apply load. Press down. Then all strain gauge readings recorded. We also record pile head settlement. So we will get such load settlement curve, load transfer curve. Of course, after your formative assessments, I'll give you comprehensive pile load test results. Pile load test informations, pile lengths, loading conditions, soil conditions, representative SPT values, load settlement curve, load transfer curve, unit skin frictions, every available result will be given for your summative assessment group project. But after your formative assessments, your first group activity, recalculation of your pi will be very simple because you've already practiced. You've done already. Just change pi length, just what I give you. But second part is numerical simulations. Exactly create your FE model in our pilot test conditions. Exactly same layer of your soil, same diameters, pi lengths, and exactly same loading steps. Then you can compare your load settlement curve and load transfer curve. And superimpose. Oh, hey, my fellows, folks, my numerical modeling looks very good because my FE results catch up with my pilot test results. It means that your project owner asks you, Hey, engineers, sorry about that. My building design totally changed. My loading condition is increased. My stories, initial one is 20 stories, but now it's 30 stories. Are you guys redesign everything? No. In your numerical simulations, increase your loading, then see what happens. And then you can increase your pile diameters. And then increase your pile length and see what happens. And then discuss with your owner, with your results. Okay, I've already tested in the project sites, and then I already created FE model. They are quite comparable. It means my numerical technique, modeling technique, very good. So you change everything. I also play around pile geometry and soil conditions, loading conditions. Still stay. I don't know how to respond. Just go ahead. This is the purpose of the numerical simulations. See what happened. What if smaller diameter, larger diameters, shorter than initial, longer than initial length? And what if suddenly we found clay layer? This borehole didn't detect the clay layer, but the main column area we found clay. What should we do? Firstly, check pile behavior along the numerical simulation. So final activities of your group project is to conduct numerical simulation using Plexis. Just single pile. Yeah, the modeling is quite simple, but the implementation of your soil properties and then abstracts the appropriate result from Plexis. Django is the famous professor in our geotechnical engineering field. In geotechnical design, it has been recognized that the assessment of soil property is the most important single task. That's why for your summative assessments, I didn't give you soil property. It means every single group adopt different soil properties. Where? Where? Out there. Research paper. Just Google. Find out research paper written by NTU professors, NUS professors, SIT professors, SUSS professor, any professors. Then you can infer the soil properties and then validate your numerical modeling. Totally open-ended project, open-ended questions. So it means that every group has a different result.